it is tradition for me to do this and say, hello, you in the room can see me, but the people who are watching online can't. And so, I'm David, this is what I look like. This is the last time you'll see me in the seminar probably. So, hello. And now you know what I look like. When you come into the Maths Learning Centre and say, oh, this great thing happened on this seminar I watched on YouTube, I'll say, yeah, that was me. And you will say, oh, yes, your face looks familiar, as opposed to, oh, really, I've never seen you before in my life. So, yeah, that's why. It's Semester 2, 2019. This is the revision seminar for Maths 1M. And I've already done the bit, for the benefit of those watching online, I've already done the bit where I've taken some requests and tried to decide an order that we're going to do that in. And we are going to start with some things on differential equations. Okay, so let's see, let me think about this. The idea of a differential equation is that it may be that the only information you have about a function is about its derivative and not about the function itself. And what you would like to do is you would like to figure out what the function is. And this happens more than you would think. So in many physics situations, you might know how the pieces of a system pull on each other, and so you know how quickly they move when the other bit moves, but you don't know actually where they are right now. And what you'd like is a function that tells you the location right now, but what you have is a relationship between how quickly they're moving, which are derivatives. And it's very similar to what happens in the engineering course called dynamics, where you actually have essentially differential equations. You have informations about derivatives, and you have to use them to figure out locations. So it's a similar idea, and it's one of the reasons it's in Maths 1M, so that people can use it in dynamics and in physics. Of course, it's a little after you have to start doing it in dynamics, but you know, it doesn't, whatever. So that's one of the reasons. And a whole lot of stuff works this way. There are things where you know that the population of say bacteria will be growing, it will grow faster if there's more of them, and so the speed at which it grows is related to how many there are right now. And so you have this equation that relates the speed to the current value, and you can use that to figure out what the current value is. So that's the idea. So information about derivatives tells you about the function. That's the sort of general idea. And specifically, an equation that involves the original quantity and the derivative and whatever the independent variable is can be used to figure out what the original function is. And it's called a differential equation. That's bad writing. It's usually with y and x and dy and dx, etc. to find y equals function of x. That's the specific idea. So not just information, but an equation. And that kind of equation is called a differential equation. And there are entire courses with the title Differential Equations that you may or may not choose to do in your life. I chose not to do them because I decided to do statistics and pure maths and Mandarin Chinese instead. I don't remember most of my Mandarin because it was a long time ago, and if you don't speak a language every day, it tends to leak out. A little bit like not practicing your maths every day, it tends to leak out as well. Okay, so I've learned all my differential equations from helping people in the Maths Learning Centre for the last 11 years. So I'm pretty good at it. And everything I know about it is to do with helping to explain it to people. Okay, so the point of a differential equation is to have something involving these things, and the goal is to eventually get to y equals function of x, or it might be y equals function of t, or it might be p equals function of t. The letters might be different. So your classic example, am I going to go through examples? Yeah. Pardon me. However, it may be that you can't do this with the tools you have, and so what you do is you figure out a method by which you can approximately figure out the value of y for a specific value of x. So we might be able to do it approximately. So maybe approximately. That's the idea. And so what you're taught in this course is some situations in which differential equations are used or have been used to solve them. You're taught a couple of methods of solving them, and you're taught one method of just doing it approximately and not solving it properly. And so they're the things that you've learned or seen. Whether you've learned them is a different question. But they're the things we've seen. And so we have methods, situations, and approximate methods. That's what we've got here. So these are the three things that you learn in this course. It looks like more, but that's how I organise them. And as far as I can tell, you've been taught two different methods. You may not think you've been taught two because only one of them has a name. But you have been taught two. Oh, actually, there's a secret method 0 as well. Okay, so the first method, which isn't really a method, is not a method for finding a solution. It's a method for checking if it really is a solution. It's always something that you can do. No matter whether you know how to get the solution, you can always check it. So mathematicians tend to call it verifying. So they might say, verify that this is a solution of the differential equation, which means that you sub it in, and if it works, then it's a solution. And that method is sub it in. So as an example, verify that y equals 3x is a solution to give me a second. 2 times dy and dx minus 6y is 0. And so you would go, all right. Oh, yep, just a second. Yes, that'll work. Okay, and so we can see if it's a solution by differentiating and subbing it in. So dy and dx, no, y was e to the 3x, so dy and dx was e to the 3x, but then because of the chain rule, we'll have to multiply by the 3. And so when I sub that in, I get 2 dy and dx minus 6y equals 2 times 3 e to the 3x minus 6 times e to the 3x, which is 6 e to the 3x minus 6 e to the 3x, which is 0. So yes, it is a solution. And that's what it means to be a solution. It means that if you do the derivatives and you sub the derivatives and the function in, it will produce the result it's supposed to produce. Okay, and that is the simplest version that I can think of, but there are others you can that might involve more complicated functions or more complicated derivatives, and that might need a little bit more algebra to show that they really do come out to the answer that they come out to. Yeah. Let me just think. Yep. Okay. So that's method sort of 0. It's not really a method of solving at all. It's just checking if what you have really is a solution. Method 1, which isn't actually, you haven't been told as a method either, is that if it's already dy and dx equals, and that's all in terms of x, you can just integrate it. So if it's dy and dx equals function of x, you can just integrate it. It's no problem. Or even d squared y on dx squared, or the third derivative, or whatever. Just integrate it. So something like this. If you saw something like that, d squared p over dt squared is 2t. Well, that's okay. You can go, well, that's just, if I integrate it once, the t will go up to 2. I'll divide by the new power, and I'll plus c. And so I've got... And then if I integrate it again, I'll get t will go up to 3. I'll divide by the 3. C will get a t attached to it because it's a constant. And that's how what constants happen. You get the variable attached plus a new thing. And that's my solution. Without being given any other information, I can't figure out what the c and d are, so I have to leave them in there. But if I was also given the information that p of 0 is 0 and p dashed of 0 is 1, then I could figure out what this was. So that's what I get when I sub in 0, and that's supposed to come out to the answer 0, so therefore d is 0. And p dashed of 1, well, I already figured out what p dashed was. It's here. It's supposed to come out to 1, which means c is also 0. So therefore p is actually 1/3 of t cubed. It doesn't always work out that they're both 0. That was coincidence. There's two things going on here. Sometimes you'll have a solution that has different unknowns in it, and you don't know what they are. And sometimes you are given extra information to try and figure out what the constants are. This is called a general solution, and this is called a particular solution. Okay, so you can always integrate if it's already just a function of whatever the variable is. So I know in my title I said y is a function of x, and I use p as a function of t, but I just want to point out that the letters don't actually have to match they don't always have to be y and x. Okay. So method 2 is designed specifically for separable differential equations. Okay. So a separable DE is one that will allow you to use this method. And sometimes, and many DEs are separable, but many DEs are not. And unfortunately, you haven't been given methods of solving things that aren't separable. And so they won't give you one unless they're asking you to approximate it or verify the solution. So I would recommend to never attempt to solve a differential equation unless the person who is asking you to do it is actually asking you to solve it. Look carefully to see if what they really want is you to verify it, or if what they really want is to find an approximate answer. There are three things that they might ask you to do: verify, solve, or find an approximate answer. Okay, so separable DEs are ones where you can separate it where you can rearrange it into this format. You can rearrange it into a part that's entirely a function of x, multiplied by a part that's entirely a function of y. Or divided by a part that's entirely a function of y. It doesn't really matter. But the point is that if you can rewrite it as dy and dx equals, then you can separate the x's and y's by factorizing into two separate pieces. That's the important thing. And if it can't be done, then it's not separable. There are other kinds of differential equations. I don't know if you were supposed to be able to tell whether it was linear or not. No? Okay, good. It seems like a pointless thing to be able to tell if it's linear if you don't know how to solve one. So there are other kinds. There's linear DEs, and there's a couple of others, but you've only been told this one because you know how to solve this. And the way to solve it is to use multiplication and division to get all the y's and the dy on one side and all the x's and the dx on the other. Because when we're doing when derivatives were first invented, the dy and the dx were separate things that could be divided. And so we are allowed to separate them as if they were things that do multiply and divide, at least when we're doing this. Most of the time, dy and dx is a thing all by itself that can't be pulled apart. But today, we can separate them. So, the easiest way is to do it with an example. Let's do that one. dy on dx is y plus 2xy. This one will be separable if I can arrange it for this thing to be a function of x times a function of y. And the only way I can do that is to factorize it. I have to turn it into things that are multiplied. So I need to look for common factors. So there is a y here, and there is a y here, so I can rearrange it to be... That's something that's in terms of only y times something that's in terms of only x. The plus 1 is fine, it doesn't matter. Because I can still figure out what this answer is based entirely on the value of x. That's the idea. So this is separable because I was able to separate the x's and the y's into separate factors. And I can solve it by moving the x's and y's using multiplication and division. I can't use addition, I have to use multiplication and division. Moving the x's and y's so that the x's are on one side and the y's are on the other. So I can do this, divide by the y and multiply by the dx. So I sort of move this over there and I move this over there. It's not really moving technically, I'm technically dividing both parts by y. So this is telling me, what this tells me is that if I move y by a little bit, then multiplying the value 1 over y by the amount that I move y, if I maintain myself being on the function that, y is a function of x, I will have to, I'll get the same change that if I change the x and multiply by this. So those little changes add up to the same thing. And so what that means is if I add up all those changes, I'll get the same answer. So I can do this. And this is very similar to what happens in dynamics, at least in the first half of the course. Second half you use like work and energy and stuff to avoid having to do all this. Okay, so now I have to integrate this. And so I integrate them separately. So I look at this all by itself and I think 1 over y dy, well that would be ln of y. Technically absolute value. Depends on whether y is allowed to be negative or not. If y is allowed to be negative, then you need the absolute values there. And the integral of this, well, the integral of 1 is x, and the integral of 2x, the x goes up to half, and I divide by the new power. No, crap, why half? I'm getting ahead of myself. 2, and then I divide by the new power. Gotcha. Plus a constant. Now I don't need a plus c on this side because the 2 plus c's would be different and I could move 1 over here and they would combine together into a single constant. So I only need the constant on one side and not both. All right. And then it's not actually finished until I have y equals function of x. And so I need to somehow get rid of this ln. And so I would normally write, if you do e to the power of both sides, then that'll do it. Very important to make sure that your plus c is included inside the action that you do. So don't do e to the x plus x squared plus a big C over here. The plus c is a proper number and we're actually doing e to the power of the thing that is here. So the c plus c has to be inside the e. And then y has to be plus or minus this, right? Because it's an absolute value. That's how absolute value works. And if we had an initial condition, like if we had something that said that y of 1 was 5, then we could figure out whether it was the plus or the minus. It would have to be the plus if y of 1 was 5 because it has to be positive. So this is finished at this stage. Most of the time when people see one that has an e to the power of c, they do this trick. So when you add things together up in the power, it's the same as multiplying them down below. And then what they do is they say all of this is a constant. And that's what most people do. I don't know if your lecturer did that, but it's something that I'm familiar with. Yeah, and it means you don't have to worry about the plus or minus because either a is positive or negative. So this is a classic way of doing a separable DE. So just be aware that a separable DE cannot have any x's in it at all. Can be just that, for example. dq on dt is q. And that's still separable because it can be written as this. Q times 1, where q is a function of q and 1 is a function of t. I know it's a function of t because I can calculate what it is based on the value of t. If t is any number I like, it's always 1. So it's a function of t. And so you would do this. You would divide by the q and you would multiply by the dt. And so you would get ln q is t plus c Let me give an initial condition for this one. I'll put an initial condition up there. So I can do e to the power of both sides. I can pull the e to the power of c out, and I have q equals plus or minus e to the power of c, e to the power of t, which means that q is actually some multiple of e to the power of t. And the reason why this is better is because I don't really care what c is, because I just want to figure out what goes in this position. Because now I can say, all right, q of 0 is a e to the 0, which is just a times 1, because e to the 0 is 1, which is just a, and that's supposed to be 8. And so the a has to be 8. It's supposed to be 8 because of this information here. And so therefore q is actually 8 e to the t. And we're done. And I didn't have to figure out what c was, because I could just figure out what a was instead. Okay, so those are the methods that you're given. Presumably there are, I keep using these ones because they're the ones that are in my head, but you can make up ones, right? If you knew that dq on dt was like t sine q, and all sorts of weird ass crap would happen. Oh gosh, don't like it. Not that one. Okay, cool. Now just remember that sometimes I want it in, this is an explicit answer here. Back here, that's an implicit answer. And sometimes they say it's okay to leave it in implicit form. So the explicit form has y equals thing, or q equals thing, or p equals thing, whatever it is. The implicit form is just once you've gotten rid of all the derivatives, that's the implicit form, and you can stop there. Okay, cool. Now, before I move on from this, can anyone think of any situations that they've been in when they've had to solve a differential equation where they didn't know what to do and they'd like to know what I would do? So basically, any examples you want me to go through before I move on from actually solving them? All right, cool. So how about we look at some of these situations? So there are two classic situations in which you find differential equations, and you need to be able to link up the information that you're given to where that belongs in the differential equation. And interestingly, one of them, they sort of solve the differential equation for you and expect you to be able to just use the answer, which defeats the purpose in my head, but anyway. So there are two situations. One situation is population growth or decay, or just actually just growth or decay. That's one. And it tends to go something like, a lake contains 100 fish. A year later, there are 120 fish. If the same rate of growth continues, how many will there be in 6 years' time? That sort of thing. Or something like in 2 years' time, let's go months. How many after 1 year? The grammar will be better, of course. This is a classic population growth thing, and so instead of just being given a raw function, you have to make the function yourself. That's the situation thing. And so what you do is you assume that the growth of the population is exponential because that's the only kind that you have. There are other ways, other situations, which are called the logistic growth, but this is the one we've got. And so we're going to say, well, how does this work? Well, so we're going to set up the differential equation. The rate at which the population is increasing is some multiple of the current population. Because you imagine saying, well, the birth rate is that every pair of rats on average, if every pair of rats on average produce one rat, then you've got half as many as you had before. It's that sort of thing. And so that's the idea. And so you'd probably have to say, let PT be the number of rats at time t in months. You need to tell the reader what the letters stand for. And you can set it up like this. And then if you solve the differential equation using separable DEs, you will get to this. Now I'm pretty sure that your lecturer actually expects you to be able to just remember that this is what is going to happen. But if you do the exact same working I did before, it will produce this answer. The only difference between this and what I did just here with my Q's is that I have a KQ instead of just a K. So this one is a K, so this one is a K, so this is a K, so we get KT. That's what's going on. So I've skipped that part, and I'm pretty sure your lecturer is okay with you skipping that part unless they explicitly ask you to prove that this is the answer. Or if you can't remember the answer, it doesn't take too long to figure it out. Okay, so the problem with this is it has two unknowns. We don't know what the K is, and we don't know what the A is. And so we need two pieces of information to figure two things out. And we do have two pieces of information. We have the population at time 0 and the population at time 2, and that should be enough. So P of 0 is 600. So we get that 600 is A e to the k times 0, which is A times 1, which is A. So the A is 600, and so therefore we actually have that P is 600 e to the kt. And also, P of 2 is 700. And so 700 is 600 e to the k times 2. And we have to solve that to figure out what k is. Technically, we don't actually need to know what k is. We just need to know what e to the k is, which is a neat little trick, actually. I'm just going to leave it as k times 2 if you don't mind. Now, you ready for this magic trick? If I do to the power of a half on both sides, that'll get rid of this 2 here. Because power times power to the power of power is power to an exponent, you multiply the exponents, and so we get that 7 over 6 to the half is what e to the power of k is, which means that 7 over 6 to the half to the t is what e to the power of k to the t is. And so therefore, e to the power of kt is 7 over 6 to the half of t. And so p is actually 600. I don't need to know what e to the k is. And this is very nice, and I don't have horrible decimals in it. So I rather like this version. I think it's cool. If you did want to know what k was, just as you know, then you could do this. Back at this stage, when we have 7 over 6 is e to the 2k, we could have done ln on both sides and divided by 2, and that would be what k is. So we could have done that if we wanted and find a decimal answer for that. If someone did say, what is k? Yeah, just in case. So we haven't quite finished the problem yet. We have a formula for what p is, and we want to know what it is after 1 year. It's not been specified. It says after 1 year. It hasn't really specified, is it 1 year after the 2 months, or is it 1 year after the beginning? I'm going to say after 1 year from the beginning, because they didn't specify. So I'll just tell them what answer I think it should be. So that's p of 12 because it's measured in months, which is 600 times 7/6 to the half times 12, which I can now use an ordinary calculator, or since I don't have one on me, Desmos. Well, it was to the power of half of 12, right, which is 1,512.9. All right, so approximately 1,513, roughly. Sorry. 513. It is just a model. Now, some people would go, oh, but it's not quite 513, it's only 512, but it's just a model, honestly. So just round it off in the ordinary way. Like, it's not like it's going to be exactly 1,513, really, because rats don't really reproduce at exactly that rate all the time. So it's just an approximation anyway. Okay. So that's the first kind of situation that you might be in. And the second kind of situation is Newton's law of cooling. And Newton's law of cooling is when you have an object and it's got its own temperature, and it sits in a room or a place with its own temperature, and the place's temperature, the place is big enough so that the small object isn't going to change the room's temperature, but the room's temperature is going to change the object's temperature. And so that's the idea. It's not necessarily a room. And then you track we track the changes in the object's temperature. That's the situation. Okay? And so there are bits of information that you need. You need to know what the place's temperature is, and I believe they call that the temperature of the environment, or the ambient temperature. Yep. TA. So this fixed temperature here is usually called TA in your notes. I hope that's what your notes say. Hoping your lecturer used the same notation as the notes. They don't always. And this changes in the object's temperature is normally called just T. Right, capital T. And then time is little t. And that's little t. So I'm just going to put a box around this so that the other stuff doesn't. Right, there we go. That's TA, that's t, and that's little t. And as we have learned, maths is case sensitive, so little t is different to big T. Okay. And there's a differential equation that goes with this too. So apparently Newton, he invented calculus, so I guess he has a right to make differential equations. So apparently Newton created this equation that says that the rate of change of the object's temperature is some multiple of how far the object's temperature is from the actual temperature of the room, where k is a positive number usually, but it doesn't matter. So it usually means that if you're above the room's temperature, your own temperature will start to decrease, and if you're below the room's temperature, your own temperature will start to increase. And it will increase faster if you are further from the room's temperature. The closer you are to the room's temperature, the closer this distance is to 0, the smaller the rate of change will be. That's what that means. So you can do a separable dE to this to get to this formula. Okay. And I believe this C is actually TA minus T naught, I think. Pretty sure. But it doesn't really matter. And you're allowed to use this formula straight up exactly as it is, without actually doing the derivative. So I'm just going to do this. It's actually that. It turns out that that constant is this. Right. Where T naught is T at time naught. That's what this is here. So apparently you're allowed to skip straight to that if you want. Okay, so we have an example. And they usually wrap it in a cutesy little story about, you know, there was one that one of the lecturers used once about someone took your beer out of the fridge and left it out without being very rude and didn't put it back, and so you can figure out how long ago the beer was taken out by what the temperature is, and it's just stupid. And one thing that you use, and there's another classic one which is like there's a dead body, and you come and you go, well, how long has this person been dead for? So we calculate their temperature. We calculate the temperature of the air, and we go, well, the moment they die, their body temperature would be 37 degrees, because that's what it is for ordinary people, and so we can use Newton's law of cooling to figure it out. Because it doesn't really work that way, because dead bodies actually still generate heat of their own for a little while, but whatever. It gives you an estimate. It's an estimate. Everything's an estimate anyway. And the other one is normally, anyway. So like a pot. This pot is taken from a kiln. It's placed on the bench to cool. And so the kiln, let's say it's probably in the couple of hundred, right? About about 400 degrees probably in a kiln. That's just, I don't know, an oven only goes up to about 200. So to 50 degrees Celsius. So assume the pot is that temperature. You know, after 2 hours, the pot is still like, I don't know, 150 degrees. I have no idea how fast this is supposed to happen. I'm just making up crap. We need to know what the temperature of the room is. Yeah. Is 27 degrees Celsius. How long until the pot is, say, I don't know, 35 degrees Celsius, just cool enough to touch, right? Not quite. You'll probably still get a little bit of a burn, but it's safe enough to just move it over if you need to get something out. So that'll do. Okay. Okay. Right. So we know that this is a Newton's law of cooling situation. So we can say let T be the temperature of the pot. And we can say that TA is the environment, and so that's 27 degrees. We know that T0 is the original temperature of the pot, which is 250 degrees. And we know that at time T in hours. So we need to tell the person reading it and ourselves what the time unit is. We're going to do it in hours because we were given in hours to begin with, so that's reasonable. Okay, we also know that T at 2 hours was 150 degrees Celsius. Okay, and we also know that T is TA plus T0 minus TA times e to the kt for some k. Because that's the formula that Newton's law of cooling provides via the differential equations. Okay, which is 27 plus 150 minus 27, which would be 123. Okay. So we know that the only unknown in this story is actually the k. In the other story we had two unknowns, but this one we only have one unknown because we've actually already used the information about the initial temperature to get this bit just here. That part of the work's already been done for us. So that's okay. We can skip that bit. And so we can say that T of 2 is 27 plus 123 e to the k times 2, which is supposed to be 150. I still find it remarkable this whole thing works in degrees and you don't have to switch to Kelvin or something for it to work. But I think it's because it's all relative. It doesn't really matter. Okay. And so I've got that 123 e to the k times 2 is... Oh, no. So T0 was 250, wasn't it? Whoop, 223. Sorry. This was 250. Right. Whew. Okay, so e to the k times 2 is 123 on 223, which is not going to simplify, which means that e to the k is, oh look, I did a 2 again. I really should have chosen a different answer. Can I change my question? I'm going to make it 3 hours. Right. I just don't want to do the same one twice, because it's, you know, beware of the toast, which means don't follow examples, don't only follow examples, right? And so if your examples have something similar, then you'll think that that's something that's always happens, and so you need to have examples where things are different. So, right. And so therefore, t is actually 27 plus 223 times 122 on 223 to the third of t. Right. Because we do this e to the k to the power of t. Okay. So now I want to know how long until it's 35 degrees. So we're going to have to solve that. All right. Which is distressingly negative. No, it's not. It's all good. I thought that I had a negative number. So 35 minus 27 would be 8. So 122 on 223. It would be very nice to get rid of those 223s, but this one's trapped inside the power, so I just can't. So if I do ln on both sides, ln of this, the power would come down. So I can do that all in one step. I won't, but you're allowed to. So you are allowed to do this in one step. You don't have to do the intermediate step if you don't want. And so the t is this. And that's what a calculator is for. I should probably use a scientific calculator. Oh, it was a third, wasn't it? It was 123 on 223, I think. Yep. Which is 16.78 according to my calculator. Hours. So, I mean, I could round it off to the nearest whole hour if I want, or I could do it in hours and minutes, which is not too bad. Which is 16 hours and 47 minutes, approximately. Times the 0.78 times by 60 to get the 47 minutes. All right. So tomorrow, if you're the potter who's baked your thing, you won't be able to touch it till tomorrow. So, therefore, based on the little quick calculation you did, it's safe to go to bed and worry about it tomorrow. Okay. So what that leaves with the differential equations is the approximate method, which I might as well cover, so I've done it all. Don't forget the rules, which are you are always allowed to interrupt me and ask me questions. It's your revision seminar. Yep?
I was remembering that, wasn't there some kind of situation where k was like negative, but there was
Yes, k can turn out to be negative, yes. But I think even if you... So if you've got something that you know is decaying, you often make the k, you write minus k instead of plus k. But it doesn't actually matter if you put the wrong one in, because if you put a plus k in your formula, it might just turn out to be negative 6.8. And then that'll be okay, you just sub the negative answer in at the end. So it's not actually necessary to put a minus in for your k. Yeah, so you can probably safely forget that. But in general, the k will be positive if it's growing and negative if it's decreasing. Yeah. Okay. Cool. So our approximate method, we only have one approximate method, which is called Euler's method. I'm pretty sure that's in this course because someone wrote it on the list. Yep. Euler's method is the method that is mentioned in the film Hidden Figures, which is about the women who did the maths to get the moon people to the moon. And so the main character in that film, they were trying to solve this problem that would allow them to figure out how to get the correct thrust to get the thing to land in the ocean. And she went, no, we don't need to come up with a new maths. We can use Euler's method, which is really old. It's a big scene. It's really cool. Yeah, anyway, so there you go. Euler's method is now important because it's part of popular culture. Right. So Euler's method is a way of not solving a differential equation. That's what it's for. We avoid actually solving it, and what we do is we just figure out the approximate answer we want. Approximately, and if we do it well enough, it'll be within whatever number of decimal places we like, and so it'll be good enough. So Euler's method goes, you have to have your differential equation written in this form. It has to be in this form, dy and dx equals something. It doesn't matter what that something is. It can have x's and y's in it. It doesn't matter. But as long as it's dy and dx equals, then you can use Euler's method. And it's not hard to put something in that form, but it's just important that it has to be in that form in order for it to work. Okay. And we normally rewrite it in this form because it's shorter. Okay, so you need d in that form. And this thing, just a moment. Oh, wow. In past courses, yep, this something is allowed to have both x's and y's in it. So this something is some function of both x and y. That's what that means. Something with x and or y. So that's what this means. So it's not, this f is not the same as y. This f is the name of this formula here. Okay, whatever that formula is. And what you do is you notice that when you are close to your function is almost the same as a straight line. So this is x e to the x. And if I'm very close to this, it's a straight line. Oh, I wonder where I put that online. Anyway. Right. So this is a curve and we have a tangent moving on it. And if you're very, very close to the function, you can't tell the difference between the function and its tangent line. They're almost the same. And so what that means is you can approximate your function by using the derivative, the value of the derivative at this point. Okay. Now the approximation's better at some places than others. I'll just go back there. So over here it was fine. But if I was down here near the turning point, I have to go in quite a bit further to get to that point where I can't tell the difference. So that's the idea. It's sometimes better than others. Okay. So the way Euler's method works is you say nearby to x equals a, y is equal to y dashed at the point for the sake of Frel. Just a second. Damn it, just a second. So at the point a, y of a, so that's us thinking that we are thinking of y as the name of a function that you sub a into. The tangent has slope y dashed a, and that tangent line is approximately the same as your function when you're very close, and so close to this point. Just a second. Sorry. So it starts at the height ya, at the point A, and then it moves off with this slope. Like that. I'm just going to draw a picture of that. Here's A, here's YA, and we are at this point, and here's my tangent. So we move this far, which is x minus a, and then since the slope is that, we have to multiply the derivative by the distance we moved to figure out how far we went. And so we started at the height ya, and we moved xa, which means we had to go up by y dashed a times the distance we moved, which is what this formula is here. Okay? And so that is approximately the same as the equation of the curve. So what most people do is they normally replace this by the letter h. And so I'm going to write that too. Sorry, I'm making this one up as I go along, so you bear with me. So if you move h, you go up or down by the slope times h, because that's what slopes are. And so therefore y equals the original y plus y dashed a times h. And so the new picture is this. Here we are at that point. That's the line. We go this far, and then that means we have to go up by this much. Because it's a slope, right? This divided by that has to come out to f dashed a because it's a slope. Okay, and Euler's method is based on this. If you are very close to the point where you started, then this line equation is approximately equal to your function's equation as well. So I can use that line equation to figure out what the next point is. And so in my head it normally goes like this. The new y is the old y plus the old y dashed times h. That's how I think about it. Yep. So all of that was great, and it's the sort of thing that if I'm the sort of, I had to derive the product rule in my first year exam because I couldn't remember how it went, but I knew how to do it. So this is the sort of thing that I could figure out how to do Euler's method if I had the picture in my head. So if that helps you, then that's great. If not, then you can remember this thing. I'm also good at having mantras that I say in my head. So I just repeat the same phrase. So that's sort of that. So what that means is just going to look for the normal wording. Use Euler's method with, I don't know, 5 subintervals. I don't really want to do 5 because I don't have time. 3 subintervals to estimate y of 1.2 if y of 0 is, say, 7, and dy on dx is x plus 3y. And this is the classic. You don't actually have a method for solving this kind of differential equation. If it was x times 3y, it would be separable and you'd be able to do it. But you don't have a method for this one. And so Euler's method is the go. I'm sure the one in Hidden Figures was more complicated than this. Though this whiteboard is about the right size. Okay. So what we have to do is we have to say, well, what's the h? What's the distance I'm moving? And then I can use this formula, new y is old y plus old y dash times h, to figure out what each new y is in turn. And most people do it in a little table, but it doesn't really matter. But first I'm going to draw my picture. My picture is this. Here is 0, here is 1.2, and the value of y here is 7, and the value of y here is what we want to know. And I want to divide this into 3 subintervals. So I'm going to have to divide this width by 3, which happens to be a neat little number of 0.4. So 1.2 divided by 3 is 0.4. So this is 0.4 and this is 0.8. Okay. Cool. So I need to know, in order to calculate this, I'm going to need to know what the old y is, what the old y dash is, and what the new y is. And so I have a table that has all of those things in it. And I will also need x to say which x position I'm at so that I know when I get to the end. So when x is 0, the y is 7, and the y dashed, well, y dashed is x plus y, right? X plus 3y. And so the answer is x plus 3y is 21. And so the new y will be calculated like this. It will be the old y plus the y dashed times the h, which is 21 times 0.4 would be, or 21 times 4 would be 84. So it's going to be 8.4. So we're going to get 15.4. It's going to go up pretty quick, people. Okay. So now here at 0.4, which is my next x on the diagram, the y, we just figured it out, it's 15.4. And the y dashed is the x plus 3 times the y. Oh, crap. So 3 times 15 would be 45. We actually have 4 lots of 0.4, which is 1.6. And so the new y, whoop, the new y is the old y plus the y dash times this. And I'm not going to do that one in my head. So what is it? 15.4 plus 46.6 times 0.4. All right, we're nearly there. The next x on my list is 0.8. And the y, we just figured that out. It was 34.04. So the y dashed is the 0.8 plus 3 times 34.04, which is awful. Which is now 102.92. Wow, it's getting bad. And so the new y is the old y, which is 34.4, plus the y dash, which is 102.92 times 0.4. What was the old y? 34.4? Oh, 04. Well done. Which is apparently 75.208. No, that doesn't make any sense. So what are we looking at? We've got 34.004. Yeah, that's all right. And my new y is the next one, right? It's right at the end. So I'm already there. So just if I really want to be things, so here we are at 1.2, and the new y is 75.208, and we're done, because that's what we wanted to get. So I don't know how approximate, I mean this could be extremely approximate, so I'm only going to go to one decimal place. So y of 1.2 is approximately 75.208. And that's how I would do Euler's method. Yeah, the new y is old y plus y dash times h. I find the easiest way of thinking about it. There you go. That's everything that it's in differential equations in this course, as far as I'm aware. So, have I missed anything? Does it feel like I've missed anything?
So, first order separable variable, is that just the same as what makes something first order?
Yep, that's worth pointing out.
Yeah, that's speaking about first order business, and we were learning about it in course.
So just some terminology. The order is the highest derivative. So this is something like that, is first order because it's got a first derivative in it. Whereas this one second derivative second order. So you have only learned how to do first order separable.
Yeah, and we've only learned how to do first derivative.
Well, technically you can do this one because you can differentiate it once and integrate it once and then integrate it again. So you can do second order or any order as long as this thing is all in terms of the variable that's on the bottom of the d whatever. So yeah, you can do any order as long as it's that, but nothing else have you been taught how to do. The only other ones you know are first order. Yeah. So yeah, technically we only know first order separable. And I don't even know what second order separable looks like. Don't really know. Yeah. That's a good question. Okay. I think that's the most comprehensive thing on differential equations I've ever done. I'll put that one at the top of the differential equations section on the website. I try and put the best ones at the top. I have this, I said in the revision seminar earlier today, I have this sort of revision seminar hoarder syndrome where I just don't like to get rid of any of them. They're all there of varying degrees of quality depending on where I was in the day and how tired I got and whether I got to prepare. Okay, whew, that was a lot. Maybe I should talk about some of the things. I reckon I can talk about a few of these things in the few minutes I have left. I can talk about complex polynomials. What do you want to know about these complex polynomials? Whoever said that? Are they still here? Does anyone here want... I mean, several people put up their hands. So what might you want to know? What was confusing? Or can I skip it? Do something else. So if you had to just yell out which one, all simultaneously, what would you pick? Fabulous. All right. I'll talk about the inverse functions. What about them?
I wrote that down and I just forgot the general method, or like sometimes I was getting confused between inverse functions and derivatives. But I don't know, I was hoping just for a quick recap of what inverse functions were and what's the method to actually do them.
Unfortunately, there's no real method, so inverse functions. But there are a few. So inverse functions, the point of an inverse function is to undo another function. And so you have one function and you go, you give an x and you figure out a y and you use f to get there. And the inverse function comes back the other way and takes the answer and produces the original input. And the reason we learn about them is because for some famous functions we need to know what their inverse is. And I've already been using an inverse function in the seminar today. I've used ln and e to the power of inverses of each other. And so the idea of an inverse function is that if you do f on something and then you do f inverse on the answer, you get the original thing back. That's the idea. And so this is pronounced as f inverse. You could say f to the minus 1 if you want, but it's not really a power. I mean, it's not like you can really do powers of functions. Unfortunately, we write the action of doing functions as if it was multiplication, but it's totally not multiplication. It's usually something way more complicated than that. We write it as if it was multiplication, and so back in the day, when all these notations were invented, we borrowed the multiplication notation for inverses, which is to the power of minus 1. Like 2 to the power of minus 1 is 1 over 2. We borrowed that notation to apply it to functions, and now everybody's a little bit confused. But unfortunately, that's what we've got. Okay, so if you have two functions that do this cancelling out with each other, then they're called inverses. It works the other way too. Usually you put a y in this spot, but it doesn't really matter. So if you do f inverse of y first and then do f, you should come back to where you started. Okay, so that's the general idea. They should, in inverted commas, cancel each other out. Right, so some classic inverses that we've seen. If f of x is x squared, as long as x is positive, then f inverse of x is root x. And I've been confusingly used x as the inside of both of them, but that's tradition. It's just the way we do it. And the reason this works is that, just to check, f of f inverse x is root x squared, which is indeed x. And f inverse of fx is square root of x squared, which is indeed x, if x is positive. If x was negative, the square root of x squared wouldn't be x. It would be minus x. So, yeah, if x was negative, if you had like minus 3 for that x, you'd square it, you'd get 9. You'd square root it, and you'd get 3, which is minus 3. So, yeah, that's why this one needs this rule here. So, yep, that's your classic inverse. The other classic inverse is that if f of x is e to the power of x, then the inverse is ln of x. They cancel each other out. They're a classic inverse. And the other, and we can extend that, if f of x was like 2 to the power of x, then f inverse would be log base 2 of x. So these are ones we have. This specific name of the exact function that undoes 2 to the power of x is log base 2. That's exactly what it's designed for. To the power of 5 is 32. So what that means is, just to draw a picture of it, if I take the number 5 and I do the action of 2 to the power of dot, 2 to the power of thing, I get 32. So what that means is the inverse goes back this way. So if I do log base 2 of thing, it should take 32 back to 5. Yeah. So that's the idea, and I actually find this picture is the most useful way of me getting that right. Okay. And the classic inverses of the trig functions if f of x is sine x, as long as x is between minus pi on 2 and plus pi on 2, then f inverse of x is called, here in this course they call it arcsine. Yep. But on your calculator it's just called sine inverse. Yeah. And then there's also arccos and arctan. So there are classic inverses for our famous functions. They need inverses, and so we give them inverses names. It turns out that, in fact, logarithms were invented before the number e, and so they have their own name rather than just being e inverse. Yeah. And so arcsine, in something like MATLAB, you would need to write just a sine instead of arcsine, the a for anti, or just short for arc. And these ones technically don't have inverses. Like, the problem with sine is that if you knew that sine of x was 1, there's lots of angles that produce that answer, and so the inverse isn't going to be able to go backwards properly because you can't, oh, sorry, I've got an alarm going off. The inverse won't be able to go back properly because you don't know which one it came from. And so what we have to do is say, well, when we do arcsine, it only produces answers in this zone. Yeah. So just as an idea of that, we know that if we do sine of pi on 2, and we do sine, it produces the answer 1. And if we do sine of 5 pi on 2, it also produces the answer 1. And sine of minus 3 pi on 2 also produces the answer 1. These all produce the same answer. So when I go backwards, which one am I going to use? That's the question. And so this function isn't one-to-one. So it doesn't have technically an inverse. And so what we do is we say that actually the normal sine function does, but if I only use this part of the unit circle, then I can decide that it always produces one of those answers and the whole inverse thing works because none of these angles actually exist in my story. That's the idea. Yeah. So just so you know, if f of x is cos x, we choose the x to be between 0 and pi. And if f of x is tan x, we choose the x to be between minus pi and 2 as well. Right. There are classic inverses, and you should know, like I just draw a picture here, it has to produce these numbers on the unit circle. For cos, it produces these numbers, and arctan produces these numbers. And you may notice, and it's really cool, that arc sine produces angles where cos is positive, and arc cos produces angles where sine is positive, which is convenient for all sorts of things. Okay, so these are our classic inverses that we have names for. Everything else is just called F inverse. And so if I want to find F inverse x, then what I'm going to have to do is find a rule which allows me to come back from the answer to figure out the input. And I'm allowed to reuse any of these famous inverses. Yep, we're allowed to reuse any of those famous inverses. And so, for example, something like that, which is the classic one that people find hard. So I have to figure out how to, from the answer for this, figure out what the original x was. That's what an inverse does. And I find this to be the easiest way to do it. All right, that's the question. This is what f is. Find f inverse. And I'm going to let y be f inverse of x. And I know that's the reverse of what you'd normally do. You'd normally say y is equal to f of x. But I want to find a formula for f inverse in terms of x. So that's the function I'm interested in. So that's the function I'm going to call y. And then I'm going to do this trick. Well, I know that if I do f on both sides, it will cancel out the f inverse. Like that. So I do f here and I get f of y. I do f here and I get f of f inverse of x. And f inverse cancel each other out. And I get x. So I'm going to even put that line in. But f of y is what I get when I put y into this formula. So if I want to figure out what f inverse is, I have to figure out what y is, because y is f inverse. So now I'm going to rearrange this to get y equals, and it will be the answer. Ooh, okay, most annoying thing is the fact that the y is on the bottom. And so I'm going to multiply both sides by that to get rid of that. And now the annoying thing is that the y's are on opposite side of the equals, and I really need all the y's to be on the same side because I just need a single y. And this y is trapped inside this multiplication, so I'm going to have to get it out in order to move it. Okay, and now I would like the y's to all be on the same side at least. I prefer there only be one of them, but you know, at the very least I can do this. And I suppose I could move that too as well, that would be okay. So now all the y's are here, and everything that doesn't have a y is over there. I would really like there to only be one y on the paper, and I can arrange that by factorising it. And now, if I divide by this, I'll just have y. Ta-da! Magic. I don't like there being quite so many minuses in that story, so I'm going to multiply the top by -1 and the bottom by -1 because this appeals to me. So that's what I did. So I multiplied by that. And that's what I have. Beautiful. So f inverse of x, because that's what y is x plus 2 over x minus 1, which is the same function I started with, which almost never happens. But anyway. I really want to draw it now, just a second. What was my function? X plus 2 over x minus 1. Oh, I'm zoomed in a lot, aren't I? So that's where it is. Aha. So to figure out what the inverse is, I should be flipping over the line y equals x, and this graph is perfectly symmetrical around that line. Beautiful. Oh. So it's quite rare that a function is equal to its own inverse, but sometimes it happens. I just want to check that this is working the way I thought should. So check f inverse of f of x should be x, right? And so that would be putting the formula for f of x into the formula for f inverse of x, like that. And if this works out to be x, then it really is the inverse. That fractions within fractions freak everybody out, but that's okay, because if I multiply the whole top of this fraction and the whole bottom of this fraction by x minus 1, that will get rid of the bottoms of those fractions. And so I will get x plus 2 whoop, that's supposed to be a minus 1. Sorry. Plus 2 plus 2x minus 2, x plus 2 minus x plus 1. It's not working, is it? No, it is! Oh, it's so cool. Okay, so that's 3x, because the 2's cancel, and this is just 3, and we get x. Oh, it's beautiful. Okay, so this function is its own inverse. So I could totally see that as an exam question. Now, I did not write the exam. I have no control over the exam. But if I was writing the exam, it would be so cool to say, here is f of x equals this. Show that f of x is its own inverse. And you could do it by finding the inverse, or you could do it by subbing it into itself and seeing it comes out to x, and that would also do it. And that would be sweet. I think that would be beautiful. And I'd be so excited marking it. So how many people realize they could just sub it into itself? Yes. Yeah, anyway. I shouldn't be as excited by that as I am. That's the general idea of inverses. Except one final thing is probably worth mentioning that's not in the section where you learned about inverses, but it is later. So you learn about inverses like early on, like up here, and then you learn about the derivatives of inverses. Oh no, you learn about it here, that's all right. It's all good. So, was that in this course or is that in a different course? Oh, it's in a different course, it's okay. It's in Maths 1A. Right, but we do have some inverse functions that we know the derivatives of, and it's useful to know them. And so There's actually a general rule for differentiating inverse functions, and it goes like this. No, I'm not going to show you. It's too hard to write down. But just while we're at it, the derivative of arc sine x is 1 over 1 minus root 1 minus x squared, which doesn't look like it should be that, because you'd expect it to have the word sine in it somewhere, but that's the way it works. And the derivative of arc cos x is minus 1 over 1 minus x squared, and the derivative of arc sine x is 1, arc sine, I already did that, arc tan x is 1 over 1 plus x squared. The reason you would like to know these derivatives is because this one in particular is rather common as a thing you would try to integrate. And so if you try to integrate this, you tend to end up with arctans. And at the end of Maths 1A, it will come up all over the place, and there will be like an arctan in almost every exam, at least once, probably twice, because it just happens. So that's why we were interested in knowing the derivatives of inverse trig functions, just because it's, you know, academically an interesting question. But also it just so happens that they happen to help us integrate things that we didn't know how to integrate before. Right. Right, I think that's everything I can say about inverse functions. Off the top of my head. Like if I was actually teaching you your course, I would go slower and have a few more pictures. Okay. So I have about 6 minutes to go. I can't do all the parametric curves, unfortunately. I brought some tools to do it too, just in case it's the only thing people wanted, because I brought some things to be drawing them in space with. But anyway, brought some Play-Doh. And wire as well is a good one. Do you do parametric curves in 3D or only 2D? 3D. Okay, cool. That's all right then. In Engineering Maths 2B, you do parametric curves in 3D. And also parametric surfaces. So, yeah. Though that course doesn't exist next year, and so there's probably a course called multivariable calculus. And I believe that the mechanical engineers will have to do the multivariable calculus, but the civil engineers won't. So, if you're doing engineering. If you're doing physics, you have to do multivariable calculus. And if you're doing maths, you don't have to, but there's not very many maths courses in second year, so you probably have to anyway. Okay. Right. Well, while I'm on the trig thing, let me just talk about that. All I could say to you is that you have to remember the derivatives of the trig functions. It's something you must know because they'll expect you to remember them. And you're going to have to be able to combine that knowledge with your other rules of differentiation. So the basic rules are that if f of x is cos x, then f dashed x is minus sine x. Do you know what? No, that's all right. And if f of x is sine x, then f dashed x is plus cos x. And if f of x is tan x, then f dashed x is sec squared, where sec means 1 over cos. So be careful, sec means 1 over, and 1 over is not the same as to the power of minus 1 in this context. Like the number to the power of minus 1 is 1 over, but a function to the power of minus 1 is its inverse. So sec is not the inverse of cos, it's the 1 over, the reciprocal of cos. So I want to point out some things. You may notice that the derivative of tan is always positive, which means that its slope is always positive. And that's true when you draw tan. It's like that. Slope is always positive no matter where you are. And you know it. So this is y equals tan x. Okay. So the other thing is that cos x looks like this as a function. And when you are early, at the beginning of being close to 0, if you're at this point, you may notice that the slope is negative, which is why this minus here. Whereas sine, on the other hand, looks like this. And when you're early, it's positive, which is why the plus here. That's how I remember it from the graph. I mean, it is negative over here, but by the time you get there, cos is negative as well, and so it all works out. Yeah. Okay, they're your trig derivatives, and you should be able to do anything with those that you need. And you can even prove that tan x has this derivative if you want. So I can prove this one, last one. If y equals tan x, then that's the same as sin x divided by cos x. And so dy and dx I could get from the quotient rule. I could differentiate the bottom. And keep the top. No, crap, wrong way around. You always start with the derivative of the top. I could differentiate the top and keep the bottom. And I could differentiate the bottom and keep the top and divide by the bottom squared. That's the quotient rule. And so the derivative of sine is cos. And the derivative of cos is minus sine. And so what I have is cos squared plus sine squared. So that minus minus becomes a plus. And cos squared plus sine squared is always 1. And 1 over cos is sec. So that's the proof. And this is the sort of thing you need to be able to do with your trig derivatives. You need to be able to do them while doing the quotient rule, and while doing the product rule, and while doing the derivative of e to the x as well. So all of these things you need to be able to differentiate at the same time if you need to. And you also always need to be looking to see if there's a cos squared plus sine squared, because you can always replace it with 1. Yeah. That'll probably do. Are there any integrals that we did? Did we do any fancy things like where you do a trig identity in order to do an integral? No? Oh, good.
Sometimes we're provided the trig identity and then we use it to solve the integral.
Ah, yep.
But we're not supposed to
You're not supposed to.
Many trig identities currently have some provided to us.
So you're not supposed to look at like the integral of cos x all squared and go, well, there's a trig identity I could use to turn that into something I know how to integrate. You're not supposed to be able to do that sort of thing off the top of your head. Yep. They give you the trig identity. Yep. Do you need to know the double angle ones? You're sure you don't need to know?
We've used it before, but I think we're not supposed to. Is that one that we provided to us?
Ah. Okay. All right. Since they've been so clear about that, but these are the two that that I know. I probably put the cos x first because I like to put them in alphabetical order. So they're the other two. So you know how cos squared plus sine squared is 1? Cos squared minus sine squared is cos of 2x. And they have to be in this order, otherwise it comes out to minus cos of 2x. Yeah, and cos times sine is half of, like, 2 times cos times sine is sine of 2x. I love these formulas, and you use them in Maths 1A to do integrals. So you sort of do what, in Maths 1A, you sort of take what you did in Maths 1M and just do more of it, really. Except, did you do matrices in this? No. Right, except you do matrices lots. Like in Maths 1A, they separate the course into 2 separate courses, and you have 2 different lecturers, but it's all called Maths 1A. And on Monday and Thursday, you do algebra with matrices, and on Tuesday and Friday, you do calculus. Yeah, there you go. Fun. But that's the future, or possibly never. It depends what degree you're in. Okay. Thank you for being here, and I hope that was helpful to you. Don't forget the Maths Learning Centre is open all the way to the end of exams, in particular Monday next week, for example. I know that's cutting a bit fine, but just so you know. The worst thing about the revision seminars is actually having to choose from the topics people have asked for, the ones that you'll actually do. Thank you. Oh man.
You're definitely going to do better than me.
Thank you for being here.
No worries.
And for asking questions. That's important.
That's all right. I definitely fulfilled my question asking quota many times over.
Thank you. Good luck.
You too.